Hello and welcome, and in this video today we're going to look at how we can calculate bit rates. You know, we start with that raw data in binary, and we're going to look at some ways in which we can calculate the amount of information that's being processed at a time. Now, this isn't strictly how modern computers do this. There are many other factors involved, but we're just going to look at how we can calculate bit rates using some raw data and what might be considered unconventional ways of doing it today. However, this is all part of that learning process in how do screens play media. Even if it gives the illusion of life, the illusion of movement, and kind of what happens behind the scenes in terms of calculating that on a computer. So let's get into this. So let's just do a quick recap on digital displays. So we have, let's say we're going shopping for a smart TV, one that we can use for watching TV, but also using as a PC monitor. Many people do this as a way of kind of saving costs. So let's say we arrive at the store and we have three options. We have an SD, standard definition, full high definition, and full ultra high definition. They all look the same, right? But when we read their cards, they're slightly different and they have different screen resolutions. So each of these three things, standard definition, full high definition, and full ultra high definition, actually are very different, and we're going to see how in a second. So we see three TVs, they look the same, but they have these written on their cards. So what does that mean? So what is the difference? Well, resolution describes how many pixels displays can show at one time. So although the screens may have the same physical size, they may actually have very different amounts of detail being shown to the eye. So standard definition has 720 pixels in its width and 576 pixels in its height. And if we compare that against full high definition, we will see that the width of full high definition is 1920 by 1080, and that's roughly 4 times the size of standard definition, and was for a long time had been the main screen size, and most phones fall within this boundary and the next. So if we take the full ultra high definition, also known as 4K, we end up with 4 times the amount of full high definition pixels in there, but we actually end up with almost 16 times the amount of standard definition. We end up with 3,840 pixels and 2,160 pixels in the height. So you can see there's a massive difference. These screens may physically be the same size, but the amount of detail on the screen could be significantly different. Okay, and for a computer, that means that they have to therefore generate a hell of a lot more amount of pixels for a full Ultra HD than what they would for standard definition, and this can actually impact how well a computer performs. So we're going to start off by calculating how many pixels are shown on a single frame in standard definition, full high definition, and full ultra high definition, also known as 1K, 2K, and 4K. So we have covered this in class, but to do this we simply times the width by the height. So can you pause the video, go to your worksheet, and I want you to complete section 1, display resolution, and there's an example on there, and you can work out how many pixels there are per frame. So go ahead and do that, pause the video, and come back when you are done. Okay, so welcome back, and now we're going to look at the next part. So remember, when we create content to be played on screens like a video game or to stream a film, the bitrate has a huge influence on the quality that is played back to us. And a big part of that is going to be the frame rate. Okay, how many frames does the computer need to calculate, make, and render per second? So Console games, prioritizing the performance of the processor, typically performed about 30 frames per second. And the early high quality 3D game consoles would operate at this rate. And today we actually have a lot more that's considered the minimum expected standard, and that would be 60 frames per second for a modern standard for home casual gaming. So a typical PC for casual gaming at home, for people that have a lower budget and aren't necessarily considering themselves to be avid gamers, maybe something which runs at 60 frames per second. But what happens once we start getting more competitive and getting immersed more into that style of gaming, a standard set for home competitive gaming that's considered good is 120 frames per second. So that means the processor in the computer has to calculate 120 frames every second to give us the illusion of that movement happening within that game. Now, if we were to be doing this more competitively at big tournament, for high-end sort of PCs and esports tournaments, you can expect up to 240 frames per second. And these are really, really powerful computers. And the reason is that the players will get really good quality, immediate feedback on the game that they're playing, and there can be loads of benefits to this. But for us today, what we're concerned with is, how does this impact the amount of pixels that the computer has to produce every second, and what's the impact of that on the performance. So how does this impact bit rates? Computers must process lots of information at very fast speeds, but processors have different speeds and power, and the resolution and frame rate can make them perform slowly if they are set too high. So if you only have a machine that's really capable of 60 to 30 frames per second, you're trying to push it to 120 frames per second, it will probably burn out. So you have to be really considerate when you are purchasing a new machine, if it's for competitive gaming, that you need to make sure that your processor can actually handle a higher frame rate, otherwise it might not work. So, but there are other factors that we'll also look at in the next slide, but for now, can you pause the video and can you go to the worksheet and can you just do a quick recap on the frames per second and match the statements with the frame rates? Okay, try and do it without the use looking at the video, and you can check your responses after as well. Okay, so in this next section we're going to look at colour depth. So this is another element that we must add into our equation, because bitrate equals the resolution, which is width times height, times the frame rate times the colour depth. And that colour depth, as you're probably thinking, is that red, green, blue, right? Well, you would partly be right, yes. It really depends on the type of imagery being generated by the program that is producing the render of the imagery. So for ours today, we're going to look at an additional consideration, which is the file type. What's the file type doing? How does that impact what's being displayed? Now, what we're really looking at here is images that are produced not necessarily live with two compressors, but happen with sort of what we call post-processing, so how images are saved. But for argument's sake today, we're going to presume that the game that we are hypothetically playing is using either of these file types to produce compressions to generate the imagery. Okay, but it's not strictly how it's done. But for us at this level, this is what we're working with. So that considering, is it JPEG or is it PNG? And there is the difference of these images is shown here. One has a white background, but one of them doesn't. So let's have a look at what's going on. So in a JPEG image, every pixel on that bitmap, okay, is made up of red, green and blue values. And as we've seen before, each of them have 8 bits, and they have binary values. And if we're going to use that to calculate colour depth, we would simply times those 3 channels together. So 8 bits times the 3 channels is a 24-bit colour depth. But PNGs slightly different. So they do have red, green, blue, but they have an additional channel. Okay, and that channel is known as an alpha channel, but we're going to refer to it as transparency. So it has a layer to show how visible that individual pixel is. So that is also 8 bits. Now what you see on this image is it doesn't have a black background, it actually has an invisible pixels on it. So where the white is in the JPEG actually shows as invisible on this image here. As a result of that, we have to times those 8 bits by 4 because there are 4 channels, and that gives us a 32-bit colour depth. So if you're into retro games, this will be you'll really understand what, where the link with this. So what I'd like you to do is go onto the worksheet, go to section 3, and I would like you to complete the questions that are on there. So pause the video, complete that worksheet section, and then start again. On to the next slide. Okay, so welcome back. We're now approaching the last part of this video, and we're going to look at calculating bitrate. So colour depth is another element we must add into our equation because resolution, which is width times height times frame rate times colour depth, equals our bitrate. How many bits do we have to generate per second in order to show the imagery that we are generating? So we're going to use this example. A full HD TV display showing The Lion King at 30 frames per second using JPEG image compression. Now what we've got to do with these scenarios is go back through that worksheet, go back through this video and work it out. So what size is the resolution? Where do we get resolution from? Well, we know we get that from looking at the screen size, whether it's standard definition, full high definition or full ultra high definition. So we find the full high definition, what's the width and height, and then we're going to times that by the frame rate, and we see the frame rate is 30 frames per second, and we're using a JPEG image, so we know that the colour depth is going to be 8 times 3, which is 24-bit, so 24. So what we should end up with is this: 1920 times 1080 times 30 frames per second times 24-bit colour depth, and that should equal this 1.4 gigabits per second. You don't necessarily have to know the conversions with gigabits and megabits, but what I will ask is that you make sure you've got the right amount of digits down for the response. So on the worksheet there are 3 scenarios that you need to look back through and find the conversions for. Okay, and you're going to finish that, so make sure you find that sheet, and what I'd like you to make sure is that you hand that worksheet to me in class, that you add your answers to the Microsoft form. The link is on Satchel, so make sure you add those into there, please. You need both parts for me in order to be confirmed as completing the home learning, and if you are doing this at other educational institutions, then obviously you see your own teacher's response for that. Please do not leave comments on YouTube. I will not reply to them, or messages, so please do not do either of those. Just make sure if you have any questions for me that you do this on Satchel as expected. Okay, so good luck, and I'll see you in the next one.